All right, who loves graphs? Let's try that again. I said, who loves graphs? That was the most pathetic thing I've ever heard. All right, so today I am going to say exactly the same stuff I said over the last couple of days, but I'm going to say it through graphs. We'll see. That might be helpful for some of you. It might not be, but at least we'll have a pretty picture when we're done. All right, so where we're going to start is just the general idea, which we said back in the first lecture, which is if we consider a graph of distance versus potential energy. In chemistry, we're dealing with two different kinds of relationships between particles. Some attract and some repel. Whether they attract or repel at infinite distance doesn't really matter, because at infinite distance, what is their potential energy? Zero. We say it has zero potential energy at infinite distance. So whether it's attractive or repulsive, it should approach zero as the distance approaches infinity, right? But what's the difference between attraction and repulsion? What happens to potential energy as attracted objects get closer and closer together? Right? Their potential energy decreases. So if I have objects that attract each other, then my graph would look something like this. It'll approach zero at infinity, and then it'll drop. And there's no real floor, right? For attracted objects, the potential energy drops as they get closer. There's no real floor. Eventually, for any two real objects, they're going to reach a point where they're as close as they possibly can be. But we don't know exactly what that point is. But the graph would look like this, potential energy versus distance. If I have repelling objects, what happens is they come together. Their potential energy goes up. So for repelling objects, approach zero at infinity, and then just have the kind of reverse. So for repelling objects, really, zero potential energy is like the floor. It's as low as they can go. But for attracted objects, zero is like the ceiling. All right. When we talk about bonding, we're actually going to come back and use these two graphs to describe bonds, because essentially bonding involves both of these graphs sort of overlaid on top of each other. But for now, we're talking about these periodic trends, which all had to do with electrons and their relationship to the nucleus. So which one of these two graphs is going to be important in discussing electrons and their relationship to the nucleus? Alec? The one below, because electrons are attracted to the nucleus. Okay. So let's consider, I want to do this. We're going to have a nice color-coded graph in the end. So here's my axis in black. This is going to be potential energy versus distance. And let's say we make this graph and we want to explain the top to bottom trend in the periodic table in ionization energy. All right, so we're going top to bottom in a column. We decided that the effective nuclear charge, Z effective, is the same. So if Z effective is the same, the curve of potential energy versus distance should look the same for all those elements. Now, that's a bit of an oversimplification. I mean, effective nuclear charge, the way we approximated it, is really a very rough approximation. But all the elements in one column, so we'll look at the first column, all the elements in that column should have a similar potential energy versus distance curve because we're dealing with the same Z effective, so the same attractive force. At a given distance. We're going to look at the potential energy of a valence electron. All right. So we set our graph approaches 0 at infinity and then kind of drops off. All right, now I'm going to place all my elements on this graph that are in the first column. So what's the difference between hydrogen, lithium, sodium, potassium, etc.? What's the main difference? More distance as you go down. So if I consider, say, hydrogen might have a distance right about here. And then lithium, the distance to the valence electron is going to be a little bit greater. So maybe it's right here. Beryllium, or not beryllium, sodium, greater distance, higher energy level. Potassium, and then rubidium, and then cesium. So the valence electron gets a little further away. So if I were plotting each of these elements on there, hydrogen has the shortest distance between the valence electron and the nucleus. Lithium is a little greater. Now, what happens if I look at what's the potential energy of an electron in each of those? So go back to hydrogen and now trace it down. Look at the potential energy of the valence electron. It's way down there. And if I look at lithium, what can I say about the potential energy of a valence electron in lithium? Is it higher or lower than hydrogen? Higher. Well, what did we say about the ionization energy as you go down the row, or down the column? Ionization energy increases. So how come if potential energy is increasing, ionization energy decreases as you go down the column? So potential energy is increasing. Why is ionization energy decreasing? All right, so the ionization energy is how much energy it would take to release it. In other words, the ionization energy is really the distance from where it is to the ceiling. Because if it goes to an infinite distance, the potential energy would be 0. So ionization energy really is how far is it from where the element is to get up to a potential energy of 0? So the higher your ionization energy, the lower your potential energy. And if we look at all the rest, sodium, higher potential energy. And then potassium, even higher. Rubidium, even higher. And then cesium, way up high. Maria? The electrons from rubidium are further away from the nucleus. Yep. Yes, you're right. Rubidium does have a higher potential energy. That's not signified by a larger negative number. So we measure potential energy on this scale. A more negative potential energy means lower potential, less potential to do stuff. And so you see cesium way up at the top here. Its electron is so close to getting ripped off. So easy. Only this tiny amount of energy you've got to give it to take that electron away. That's why cesium, very high potential energy. Hydrogen, a lot lower. The higher the potential energy, the weaker the pull. Yes. So higher potential energy comes from having a weaker attraction to the nucleus. I may have made this analogy before. If you consider potential for drama in human events, when is there greater potential for drama? When a couple has a really strong attraction to each other, really strong bond, or when they have a weak attraction to each other. And they're just kind of like, you're all right, but something else comes along, I'm ready to jump off. Right? Weaker attraction tends to lead to more drama. So when there's a weaker attraction to the nucleus, there is higher potential energy. All right, so you're right. This graph that we just drew only applies to differences in distance, but we had to go in the same column, so the same effective nuclear charge. Next, we'll compare what happens if you have a different effective nuclear charge. Yeah. So the question is, what's going on with zero potential energy? Why is zero like the ceiling? How can you have negative potential energy? So the answer is just potential energy is always relative. So when we say zero potential energy, that's not an absolute zero. There is no absolute zero of potential energy. All there is relative potential. So if we can compare how much potential energy an electron on cesium has to how much potential energy an electron on hydrogen has, and say the electron on cesium has higher potential energy, has more potential energy. The 0 point, the floor for potential energy, there really isn't one. So there's no like absolute minimum that we can set. So we set the 0 point as being infinite distance between the two things, because that's the most convenient for us. So we've got the fact that the actual values of potential energy are negative, you just don't want to worry too much about that. You want to just focus on where are they relative to each other. Okay? And ionization energy really is the amount of energy to get from where it is vertically on this graph up to 0, even though that seems strange. Adrian? All right, so last year in bio type, activation energy is something we're going to talk about a lot this coming up in, say, January. So the way this relates to activation energy for a reaction is the potential energy, basically hill, that the reaction has to get over to get from reactants to product. And so in a reaction involving cesium, in a reaction where cesium loses an electron, the activation energy hill is going to be really low because it doesn't take a lot of energy to get that electron out of there. And then if it goes to some place where it's going to be more stable, the downside of that, the downslope of that hill may be really steep, and so it'll give off lots of energy. So if you take cesium and dump it in water, it gives off a huge amount of energy and it reacts. Because that activation energy is really low, the reaction is fast, and because the electron has lower potential being someplace else, there's a net release of energy as well. So we will explicitly talk about activation energy in reactions. Right now we're just talking about the energy, or the potential energy of an electron in the atom itself. But this will be relevant when we start talking about reactions that occur. Maria? So the graph, if I've drawn it well, it should show that the potential energy differences get smaller and smaller as you go down the periodic table from one energy level to another. So the gap from hydrogen to lithium is the biggest, and then lithium to sodium is smaller, sodium to potassium is a little smaller, and so on. Yeah, so it should show that. Now, if I had really drawn this well and to scale, the gap between hydrogen and lithium is actually enormous. It's like 3 or 4 times the gap between lithium and sodium. So I haven't drawn it perfectly, but that's because I was just drawing this freehand. But you're right, the potential energy should get closer together as you go to higher energy levels. All right. Let's talk left to right. So if we're looking at the left to right trend, all right, how do we explain the left to right trend? As you go left to right in the periodic table, we said that the effective nuclear charge actually increases. How would the graph that I drew change when you change the effective nuclear charge? So in other words, I said for attracted objects, the graph is always going to have this shape where it approaches 0 at infinity, and as you move back towards 0 distance, it falls. But how would this graph maybe change if I had a greater effective nuclear charge? So this was the graph for a z effective of 1. If I wanted to draw a z effective of 2 on here, as those two objects approach each other, now instead of a +1 and a -1, you have a +2 and a -1. As they approach each other, how would their change in potential energy be different? It would go down. Would it go down at the same rate as if it was +1? Would it go down faster or slower? It'll go down faster. Yeah. So if I want to compare a z effective of 1 and a z effective of 2, now I'm looking at two graphs, one of which is going to have to fall off faster than the other one of which the potential energy is going to drop faster than the other. So now I could do, all right, potential energy versus distance. And make another graph of potential energy versus distance. And if this one over here is, say, for z effective of 1, this one might start out there and then drop off like that. The other one is going to drop off more quickly. I don't know if well, you know what? I'm going to draw them both on the same axis. So I have one graph where z effective is 1. The graph where z effective is 2 is going to drop off a lot faster. So if I compare two elements with their valence electrons in the same energy level, so even if the electrons were at the same distance, and I look at the first element with a z effective of 1, the potential energy would be over here. So let's say this was hydrogen compared to helium. In hydrogen, the potential energy might be up here, but for helium, at that distance, the potential energy is going to be a lot lower. The reason is helium has 2 positive charges pulling the electron in. So because there are 2 positive charges pulling the electron in, the electron's attracted more strongly. And so if you think about it, it takes more energy, or the amount of potential energy is going to drop off twice as fast as the electron approaches helium. It is, all right, so good point. So the question is, isn't the atom of helium smaller than the atom of hydrogen? So yeah, I assumed, what if they were at the same distance? But they're not. In reality, helium's smaller, so in reality, helium would actually be even lower. So sure, I can redraw that to reflect the size better. Even if helium had actually the same exact size, it would still be lower potential energy. But because helium's even a bit smaller, potential energy is that much lower. Ionization energy increases from left to right. And so if you look here on this graph, the ionization energy of hydrogen would be essentially this energy there. And then the ionization energy of helium would be that whole chunk there. Again, I haven't necessarily drawn it to scale. I'm not drawing it with the actual numbers. So when you're thinking about the potential energy of electrons in different situations, essentially ionization energy is like the reverse, the positive value of the potential energy of the electron. So a higher ionization energy actually means a lower potential energy for that electron. And the good news is, I'm not going to test you on this graphical representation, but I think it can be useful. If you look in textbooks, you'll see graphs like this. It can be useful to have an understanding. So if at least 2 people really enjoyed that presentation and took something away from it, great. And if you didn't, I wouldn't stress out too much. But at least we have this beautiful rainbow-coated picture. All right, so let's do our checklist. Take a minute to read the objectives. All right, so let's check our understanding. Identify the valence energy level and number of valence electrons for any atom. Can I check that one off? Explain atomic properties based on the number of protons in the nucleus and the energy level occupied by the valence electron. Okay, so question about identify the valence energy level. That just means identify what energy level is the valence level. So, for instance, in carbon, the valence energy level is 2. Energy level 2. That's all that means. Yep. So explaining atomic properties based on number of protons and the energy level occupied by the valence electrons. We good? Check it off. All right. No one explained the periodic trends in ionization energy, atomic size, ionic charge, and electronegativity. For Z effective, when you're going, yep, Z effective stays the same within a column. Yep. Again, that's our like rough approximation of Z effective. You may, if you take an inorganic class at some point, look at some like more complicated approximations of Z effective, but they still show the same trend, so they don't necessarily shed any more light on anything. For ionic charge, it's just, yeah, calcium would be a +2 ion, and fluoride would be a -1 ion. Yep. Well, ionic charge essentially only really applies to the first 2 columns, +1 and +2. It's somewhat to column 13, like aluminum and gallium tend to make +3 ions. And then nitrogen -3, oxygen -2, fluorine -1. Yeah, just predicting the charge. Using that octet rule as a guideline. Right. So the question is, wouldn't Z effective go down within a column because the atoms are getting bigger? Well, that's a separate effect. So Z effective is what is the charge felt from the nucleus, and then the distance is the other effect. So Z effective stays roughly the same, but because the distance is increasing, the strength of the attraction gets weaker. Yep. All right, and then the ones written by the AP people. So predict and or justify trends in atomic properties based on location of the periodic table and or the shell model. That's just their language for saying what we just said, I think. Questions about that one? Justify with evidence the arrangement of the periodic table and can apply periodic properties to chemical reactivity. We will come back and discuss that more when we talk about chemical reactions. But so the question is, what do they mean by the arrangement of the periodic table? Well, the fact that instead of just having a list from 1 to 100, we've kind of arranged it into these columns and rows. And so you should understand that things in the same row have their valence electrons in the same energy level. Things in the same column have the same number of valence electrons, the same effective nuclear charge, that kind of thing. Yeah. I mean, you also just want to know, because of the way it's arranged, based on Z effective and these trends and properties, things in the same column tend to behave the same way. So, what do you use to disinfect a swimming pool? Chlorine. All right. Who's been hiking and had to put little drops in their water that they collected from streams? What did you put in it? Iodine. Oh, chlorine and iodine. They're in the same column. They have similar properties. They both can be used as disinfectants. Bromine, same thing. A lot of times people use bromine in spas and stuff instead of chlorine. So knowing that in the same column they have similar properties. Yeah, so there's a question about metallicness. All right, so the question is why is metallic property associated with being on the lower left and non-metallic with the top right? When we talk about the bonding in metals, we'll explain why having that weak hold on valence electrons make them have those properties that we associate with metal. So an explanation for that is coming. Yep. All right, and then last, analyze data based on periodicity and the properties of binary compounds to identify patterns and generate hypotheses related to the molecular design of compounds for which data are not supplied. So, does anyone understand what that means? Because if you do, I'd like some help. We tried to put a couple of questions on the problem set that would address what we think that means. So, hopefully that, yeah. I think what it means is, if you're told compound X has such and such properties, what's another compound that might have similar properties? You could choose a compound that would have things from the same columns as compound X. But I don't know if that's exactly what they mean. Yeah, so the question is there like a curriculum list that's like, here's all the ideas you need to know? And the right, so here's the idea. The story of chem, the way that we arranged it. So if you look at the front of your notes packet, right? That's all the stuff you need to know. So in there, in boxes, it'll say AP EU 2.1, and that's what they have described as the enduring understanding that you need to take away, in their words. And then underneath each enduring understanding, there's what they call essential knowledge. So we've put them in there and indicated AP EK 2.1A, and then that's like one of the sub things. So yeah, we've given you all those. They're in that packet. I've tried to put them in a way that makes them somewhat understandable. So hopefully they're useful to you. And I do expect you to read them, because that'll help you kind of understand the wording that the AP people use. Sometimes I think their wording is really great and elegant, and other times I think their wording really muddles the issue. So the question is, what are binary compounds? Binary compounds are compounds of 2 elements. So sodium chloride, things like that. are binary compounds. So I think the idea with this last objective here is that you might be given data on a bunch of compounds, and then there would be a blank where you have to fill in, like, okay, then what would the properties of this other compound be? And it would be some combination of the elements in the other compound. But it's a little hard for us to speculate because I don't know if they've released any questions related specifically to that learning objective.